Okay, thank you, everyone. I hope the lunch doesn't kick in. You start dozing off, but that's okay. It's kind of afternoon here, so but I hope what I have is going to be useful. My understanding is this is a fairly sort of entry-level type of treatment that we prepared for. My three talks are actually taken from three different courses we have at the university. The first talk is some of the lecture material we use in our radio frequency and microwave circuit design, first course in that. And the second talk is on GaN PA design. I teach an RF and microwave power amp design class, and so some of the material is drawn from that. And then the third talk will be on wireless systems design from a very basic point of view. And that is from a course, I took some of that material from a course we teach on wireless circuits and systems design and analysis. So mixed in some ADS, a little bit of monolithics examples, so that's what you're in for the next hour and a half. So in this talk, we're going to go over matching network design basics, starting with lumped element matching, taking an example on a PCB board, how you bring that into realistic parasitic models and interconnects and so on, and how do you go from an ideal design, sort of textbook design, to something that actually builds and works the first time on a board. We'll also just briefly talk about distributed matching from the point of view of stub matching, quarter wave matching. So in a matching network, our goal is typically to match from something that is not equal to the system impedance, which often, not always, is 50 ohms. So for the purpose of this talk, just assume our system impedance is 50 ohms, but it doesn't have to be. And our role of the matching network is to obtain gamma in equal to 0 at the input reference plane here. Okay, if that's provided that gamma G equals 0 or ZG is equal to the system impedance. If it's not, then our goal might be a little different, and that is to match to a Zn is ZG conjugate. Here's just an example of a PCB board match. This is something that we had a customer ask us to take a LNA surface mount amplifier that was actually had a reference board that had a 2 gigahertz matching circuit already built up on it, but our customer wanted to use it at 2.3 gigahertz. So we were able to set up the models for this, get reference planes for the S parameters of the amplifier shown here, and then sort of adjust the values of these elements so that we could tune that board up to where the customer wanted to use it at 2.3 gigahertz, and it basically get a one-shot design. There's a paper there referenced in your notes that you can look up that has more details of that. So our goals are to of a matching network might involve simplicity. I really believe in keep it simple, and also cost might be a factor, and size. In module design, going to very, very small modules, thin layer boards, and very small components, and so that might be also a consideration. What about bandwidth? Well, a wide band design is going to be a lot more challenging to achieve a match. There's going to be a trade-off in the quality of the match versus the bandwidth and the complexity of the network that you need. Our purpose today is to keep it simple, and we're going to be talking about narrow band designs. I have a couple references at the end for broader band matching, and there's a lot of synthesis tools out there, including built into ADS and other simulators. If the circuit is matched and the matching network is lossless, then all the power is going to be delivered to the load. And one of the things that is kind of a consequence of the theory is if you have a reactive load, you're not going to be able to match that with a lossy matching network. So the types of matching networks we'll talk about are lumped element, like LC matching, and distributed element, which would be ones that involve transmission lines. So lumped elements classically are used at lower frequencies, distributed at higher frequencies, but actually as a designer, these are just tools in your toolkit, and you should be able to mix and match lumped and distributed networks. So for lump network matching, let's suppose in general you have a complex RL plus JXL, and you can match that with a simple L-section network is what it's sometimes called. And this particular topology will work for the case where the real part of impedance is less than Z0. And you might need a slightly different altered topology where the first element is a shunt instead of a series element for the case where the real part of ZL is greater than Z0. In the last speaker, he talked a little bit about a matching tool that is in ADS. I'm not going to use that tool, but how you move around on the Smith chart with series and shunt elements. I particularly like this. I have something like this hanging on my wall. When I'm solving matching problems, it really does help to understand how to move around. We don't have time to get into, if you're not familiar with the Smith chart, I'm assuming Smith chart familiarity. This is actually an overlaid Smith chart where we have, this is in ADS, where we're using what is sometimes called an admittance chart, which has the impedance and the admittance shown in different colors. So this circle here represents, the center of the chart represents a 50 ohm match. When it's normalized, that's R equal to 1. And so, or gamma equal to 0. That's where we are. And then on this circle, everywhere on this circle, R is equal to 1, or it's 50 ohms, but we have different, reactants. On this circle, G, 1 over R, is equal to 1, right? And so we can move along this circle by just adding series inductance. And if we have a different resistance, like 100 ohms or something like that, we're just going to be on a different circle. But adding just series inductance moves you this way, series capacitance this way, shunt C this way, shunt L this way. Sometimes, and you'll see some of the examples that I'll give, I'm using a standard Smith chart, and you go back and forth between impedance and admittance by flipping 1 over Z ends up coming over to the other side of the Smith chart, and we use the same Smith chart. So apologize, that might be a little confusing in these directions, but anyways, there's different tools that can be used. Let's start very simple. You have a load of 50 plus J35, and you want a Zn equals 50. This one you can almost do in your head. What we want to do is cancel that J35. How do we do that? We need an element that will give us minus J35. What kind of element is that? Series inductor? Series capacitor, okay. So it's capacitor. If we assume F equal 1 gigahertz, we can easily calculate the value. And here I've just got a little calculation sheet. And we ended up with a value of 4.5 picofarads. Should be able to do that. We put that into ADS just as a valid. We can show that this putting you see the blue circle. Here's another lumped element example. It's not. We'll just take baby steps. So the next step we'll just make it not 50 ohms but 100 ohms. Now I'm going to need a little more complicated matching network, and I can do that with the first. Remember now here the real part of ZL is greater than Z0. I showed you the topology earlier. So my first element is a shunt element, and then a series element. You can find standard textbook solutions to the analytical formula, or if you feel so motivated, you can derive this for yourself. You just do the math on it, and you solve for what you need to do to set Zn equal to Z0, given these complex values here. And you can arrive at a formula for B1 and X1 for these two values. It turns out there's two solutions. See this plus and minus right here? So there's two solutions to the problem. And we'll just look at how we might solve that on the Smith chart. So that was the analytical solution. We can just calculate it. If we plot 100 plus J35 on the Smith chart, normalized, it comes out to 2 plus J.7. We're here. We plot the R equal 1 circle, and what we want to do is we're going to add a shunt element. So when we add shunt elements, we want to be in the admittance domain. So here's where I'm going to use the standard Smith chart, go over 180 degrees over to this side of the chart, and this is the G equal 1 circle now. Now I'm in impedance coordinates, and what I want to do is I want to add shunt inductance or shunt capacitance to take me either up here to this part of the circle or down here to this part of the circle. Those are the two solutions, by the way, graphically now. So, so we'll just stick with this solution here, and it turns out that's going to end up being a capacitive solution. And after I go to this point, I figure out what value of B susceptance I need to change the admittance from this point on the Smith chart to this point. So that's a calculation I can do once I read off the values, which you're not gonna read today from this chart, but trust me, these are the right values. Then you go back to the impedance plane because I want to be in the impedance plane when I'm here. So after I add this value here to get me to this, this is where I'm at on the topology. Then I'm going to add a series element. So for a series element, I want to go back to impedance. I do that by rotating 180 degrees. That brings me back to the R equal to 1 circle. And now we can remember my graph, where what kind of element do I need to add to rotate this way on the Smith chart? Series L. And so I just add series L, and that's going to bring me back to this. Here's the analytical solution, and this is what it looks like on a Smith chart. By the way, if you got the flash drive we handed out at the beginning of the talk, it has workspaces for all and examples for each of my talks. So this is all set up on the workspace. We won't take time to jump out to ADS for each one of these. But so this is just plotting the impedance. This is an example of a little slightly different case here. This is 100 plus J100. And after I add a capacitor right here, that rotates me to this part, which is on the R equal to 1 circle. If you can see that red dot. Right. And by the way, it's kind of, well, you can use tuning to just start out with not knowing what the value is at all, and just use tuning to get to this point on the Smith chart, and then add the inductance you need to get to the match here. So what about a PCB board match? Okay, so what's different in going from that ideal world to the real world? One of the ways I like to describe RF engineering is as compared to AC engineering, because we can get an omega L and a 1 over omega C for our impedances of our inductors and capacitors. That's AC theory, right? So what's different about RF engineering? I like to put it this way. When is an inductor not an inductor? When it's a capacitor, until it's an inductor again. Because what happens with RF engineering is there's something called parasitics. And so if we take a packaged inductor, you have this nominal inductance, but a real inductor has some bonding pads, and there's capacitance between those bonding pads. Eventually, there's going to be a self-resonance, a 1 over square root of LC resonance between those elements. And then above that resonance, the capacitor is going to dominate. So it becomes a capacitor. And if that's all there is, then it would be, but it actually gets more complicated than that. So let's say that we wanted to make a low-pass filter design. I'm going to jump out to a filter design example just for a moment, and we'll come back to matching. So if I had designed a filter that looks simply like this would be a low-pass filter, because at DC the inductors are shorts and the capacitor is an open, and then at RF this is open, this is short. So now if I wanted to go towards an RF model of this, say I synthesize that filter in a filter design package, I go to the RF model. Well, one of the things I could do is I could download vendor S parameters for these inductors and capacitors. That will kind of capture the RF behavior if they're measured through my frequency. I'm still going to be missing some things. Does anyone know what it is if I just plug in S parameters here? And I try to simulate this at high frequencies? What's that? Traces, yeah. You can't just jam these components together. You know, you actually have to put, if it's going to be a PCB board, you're going to have to space them out at least a little bit on the board so you can solder and so on. And those spaces are going to have an electrical length, and there's going to be an interaction. Even if you use ideal components, the simulated result's going to change right away. So if we instead want to use a model, one of the things you can do if you have measured S parameters is you can make your own models if you systematically know kind of what to do. So in addition to the straight capacitance, if we put this on a board, there's going to be some ground effect due to this, the ground plane and the solder pad capacitance to ground. So the model starts looking a little more complicated. So let's suppose we had laid this out on a filter like this, and we wanted to model this ourselves. The capacitor has a similar story. The topology looks a little different, but these would be simple parasitic models for the inductors and the capacitors. And notice I have interconnect models for the transmission lines, a T-junction model, and the transmission lines here. One of the things often overlooked is when I ground, well, depending on your technology in your lab, and in the student lab that we use for this experiment, they actually drill a hole and put a wire to the ground. And we have an approximate model, but it does have some inductance, and so that's another thing. All right. So at our company, which is a spin out of the university, over the last 14 years, actually, we've been in business. We've developed models for over 200 RF component families, RLC component families. And these models scale with the part value. And I guess if you think about these models, you could think about the way these models are. They're much more complex versions of these simple models that I described. They model multiple higher order self-resonances, and they take into account the board effect. That is that when you place a component on a PCB board, it actually will alter its behavior. So the inputs to the model also include the board effects. So these models that I'll demonstrate here have as input the nominal capacitance. For example, this is a capacitor model, but also substrate information. And there's a simulation mode that allows you to set it as an ideal capacitor or a full parasitic model, and there's also a simulation mode that allows you to de-embed the solder pads out in case you want to combine the models with an electromagnetic analysis tool like momentum, and you want to use momentum to simulate your trace effects, including the solder pads. There's other ways. There's other elements here I won't get into. This is what it looks like in ADS, and basically what's inside is a complex equivalent circuit model. Another advantage of an equivalent circuit model is S parameters are limited to the frequency range where the measured data is taken, and if you want to do any extrapolation above and below, you have to be really careful. All right. So let me go back to that example we had. We had realized a match of 100 plus J100. I'm going to go into ADS here, take a moment to look. So this is what it looks like in ADS. Let me zoom in on this part of the circuit just so. So here's our 100 plus J100 ohm matching circuit, and we've set these models up. There's an inductor and capacitor here. These are the values we arrived at from the classic ideal solution, and the sim mode is set to 1, which sets it to an ideal model. In the second circuit, all we did here was set the sim mode equal to 0, which is going to turn that model into a full parasitic model. By the way, each of the models is going to have a model information data sheet like this. And so one of the things when you think about with RF design is you have to be thinking about the concept of a reference plane. I assume that was covered in earlier talks today. Can somebody give me a description of what the reference plane defines? Oh, they didn't go over it? Okay. So when you calculate a network analyzer, the reference planes defines the position for which, if you're making an S21 measurement, for example, that the phase is 0 degrees. Or if you get the calibration correct, you measure a perfect short circuit, then your network analyzer better report, if you're measuring a perfect short, it should report an angle of 180 degrees for the reflection coefficient, or perfect open 1 angle of 0 degrees. That's what the reference planes defines. And so it really kind of, you think about it in a component, defines your connection point for that component into the rest of your circuit. And the reference plane is critical to getting the phase right. And so that's what we're just showing you here is the solder pads and the reference planes, and this is kind of what the component looks like. The substrate effect is also can be important at high frequencies, and this is the same part value on multiple different boards. And also, the component families will have specific values. And so if you have calculated or determined on the Smith chart that you need well, as we did there, a 1.087 picofarad capacitor, probably there's a 1 and there's a 1.1, but there's not a 1.087. Probably not important. You have to go to the closest value. And there's ways to set up ADS to do discrete optimization, so it will only go to the values that are available. Or sometimes it's maybe a little easier to do a continuous optimization and then go back in and set the value. So we're going to go into what I like tuning a lot. Oh yeah, I didn't show you one other thing. Here's another version of the circuit that has the parasitic models, but now we also have some interconnects for assuming that we have maybe sort of a typical microstrip layout. Actually, let's take a quick look at the layout to show you that that's kind of realistic. Okay, so the last board, last one is this. So this is kind of a layout of the matching circuit. And what we did in each case is we put the value of the matching elements here equal to what we calculated from the ideal simulation. And I've already told you that it's going to be different. And we look at this in, let's go ahead and simulate the result. And the way that these three circuits are set up, the ideal model was set up, and that one confirms that we did our calculation right, and we have a match with that ideal model. When we turn on the parasitics on the model, just the fact that we have some non-idealities to those components, we see the blue curves, right? And I'm not sure what am I seeing that? Okay, and then this is the one with the interconnect. So pretty far away, right, from the match. So what we're going to do is we're going to go into the tuning mode. Just have no idea why it's doing that. Okay, and I'm going to find the tuning window here, and I have the LNC. So what I'm going to do, let's look at the Smith chart view, and I will just tune. See, now I'm tuning on the capacitor with the full parasitic model in the layout. So I'll tune that down about here. Now I'll tune on the inductor, and I can see that if I play around with this a little bit, I can get a pretty good match. Here's what it looks like in magnitude. This is the ideal circuit red, and the magenta was the one that I just tuned. And then when I update the schematic, we started out with 6.8, and over here we had 1.087, and it turned out that it wanted us to use 0.3 picofarads and 6.1 nanohenries to compensate for the non-idealities. So the good news is we can still realize a match. The result is that we need to use different component values, but the models and the ADS simulation tool allows us to arrive at the solution that encompasses the non-ideal effects and allows us to achieve a matching circuit. What you could do from there next is to go back to again the data sheet. See what the closest values were for we had 0.3, pretty close to 0.3. We could see 0.3 picofarad is actually available. So we could set that to 0.3. And if we look at the inductor, the inductor family, and we had 6.1, and what we have available is 6.2. So I can go back to my simulation, and I can just plug in what was it, 0.3 was available. So I can do that. And then here, 6.1, no, 6.2, right? 6.2. And let's see if that would be acceptable. Okay, that doesn't look too bad. But if you really needed to do better from there, if you didn't like that, what I would do as a designer is I would go in and I would adjust the widths and lengths of the transmission lines in that network, and I could nail this. So it's a little bit of iteration, but I wanted to kind of jump out of the sort of the ideal world and give a little more realistic example in how you might use ADS along with models of the transmission lines and so on. Okay. Sorry, I should have started from the current slide. We're getting there. Okay. Okay, so this is just a summary. If you were to tune the three different models that I showed, the ideal started out here, and just using without the interconnects, we got a slightly different solution. And then when we included the interconnects and the parasitic models, this was the final solution. Okay, so what about distributed matching? So these are also called LC networks to some degree. And so this is a single stub tuning using a series transmission line and a shunt open stub. And so if you look at some of you break it down in steps. We start at the load for an arbitrary load, RL plus J XL. If we're solving on a Smith chart, we're going to normalize that and plot it. And then we're going to rotate through a transmission line of a characteristic impedance that's given here, Z0D, and we're going to arrive at this impedance, right? So this is the input impedance, and we can calculate that analytically, or we can determine it from the Smith chart. And this is going to end up being a shunt element. And if you have an open stub that's less than a quarter wave, it turns out that that will present a capacitance, a capacitive type of susceptance at this point. If you have a shorted stub that's less than a quarter wave, it will behave equivalently or can be equated to a shunt inductance. Okay, and for our analysis, we're going to assume we're going to try to go for 50 ohms. These are the equations for going from the load to the Z and D that we show here. So analytically, we can use these equations for the input impedance of the transmission line, and essentially, it's essentially the same equation, a little different. I might have to do a change between talks here once I don't know what is going on. But anyways, this is the input impedance of just the stub by itself. And if it's a short-circuited stub, this reduces to JZ0 tan beta L. If it's an open stub, it's minus JZ0 cotangent beta L. And here we just see that if okay, so this can be equated, this JZ0 tan beta L can be equated to a J omega L for the susceptance to represent an inductive component, and the capacitance can be equated to a capacitive type of behavior. Yes, was there? Well, it doesn't have to be for the theory, but it does have to be for for the statements that I made, for it to behave capacitive, or to behave. So actually what happens on the Smith chart, the position on the Smith chart of an open circuit is over here on the right. If you rotate that a quarter of a wave, it rotates along, if you plot that open, you're going to rotate along the outside of the Smith chart. Quarter wave brings you all the way over here to a short, which this is all the capacitive side of the Smith chart. I'm really sorry about the computer difficulties. And if we then keep going beyond a quarter wave, we end up here, which is actually the inductive part of the Smith chart. So it becomes inductive at that point. Right, same thing true for a shorted stub. It starts out on the left side of the chart. Quarter wave brings you over to the open. And if you keep going, you end up on the capacitive part of the chart. Okay, so in this example here, okay, so we are assuming that we have a load, let's say it's here on the Smith chart, and we're going to identify, so what we do is we can identify a position on the Smith chart by wavelengths. It's called wavelengths towards the generator or reflection angle here. And what's a little different here than the other matching is that when we rotate through a transmission line of uniform characteristic impedance, we're going to stay on a constant gamma circle like this. And so we can rotate anywhere on this circle by rotating down this transmission line, this distance d. Yes? Yeah, I know. You know, I think maybe I hate to take a little break, but it seems like it is, can we take a little break? Can we pause the IEEE TV and resume?
Yeah, how close are you to this one? Do you want to see it now, or?
Yeah, I think so. Yeah, well, I can try to keep going, but it is about, we can try. I don't think it's just this connection, because my computer's blinking too, but we'll try. It could be this. I'll try it. Okay, so, all right, so what we want to do is rotate, so our goal is to, we plotted admittance. We're in the, now this is going to be treated as an admittance chart. So we plot, yeah. So we plot Y-sub here, and we're going to rotate over to this R equal to 1 circle. Okay, so that's what we've done here. This is the R equal to 1 circle. And that is a position now where I can add a shunt element. The capacitance is going to bring me down to a match. So, you know, so again, how many of you are not familiar with the Smith chart, and this looks really, really strange to you? Is there anybody? Okay, sorry. So there's a really good book. I really recommend the book Microwave Engineering from David Posar. I mean, there's a lot of books on this general subject, but we use that in RF and Microwave Circuits 1. It's in a 3rd or 4th edition. It's Microwave Engineering from David Posar. So, what's that? Posar, P-O-Z-A-R. Okay. So we start out in impedance, in the admittance, and then what we did here is we drew a, a constant magnitude reflection coefficient, and as we move from the load to this position Z and D, we can go anywhere on this line depending on the distance D. So we choose a distance that brings us to this R equal to 1 circle, and then we can calculate that distance by looking at the numbers on the edge of the Smith chart and subtracting the wavelengths towards the generator numbers, if you're familiar with the chart, and we can get that distance. And then the last thing we need to do is figure out what amount of susceptance we need to add to bring us to the match. And so if we look at the value of the coordinates of that point, it turns out the admittance is 1 plus J 1.4. So we need a stub that will give us a minus 1.4 susceptance. Now we can calculate that using the formula we gave in a previous slide, or we can realize that an open stub that we're doing, an open stub that we're going to use, is going to start out here, and we can find out how long that stub would have to be to give us a reactance of 1.4. This tiny number, if you could read this tiny number here, it's 1.4. And then we figure out what distance that is, and that gives us the distance of the stub. So we get these two distances, and those are usually given in wavelengths. And then if we have those in wavelengths, let's say that this one was 0.12 wavelengths. If I want to realize that in microstrip, which I don't have an example for, but if I want to realize that in microstrip, I'm going to use a microstrip calculator like line calc and figure out what length of line and width I want to use to realize that line of that length and that characteristic impedance. Yeah.
Could you simplify the difference between impedance matching using lumped elements and impedance matching using the stubs?
Okay, so the question was, can I simplify or explain the difference? Okay, as I tried to allude to early on, there are tools in the kit. So as you get to be an experienced microwave designer, you realize you can actually use them both. So what ended up happening in general for distributed matching like this, one of the things is you don't have to go out and buy any components. If you're laying out a board, you can just design the dimensions of your transmission lines to realize your match without buying any components. That's one advantage. At low frequencies, though, that 0.12 wavelengths that I gave at 500 megahertz, that's going to be really big. So it's not going to fit on the circuit board. And whereas you can realize a lumped element very much in much less space at low frequencies. At high frequencies, because wavelengths goes down with high frequencies, in integrated circuits, microwave, like MMICs, RFICs, and so on, you can get, that's very convenient to use distributed matching at higher frequencies. But again, you can use both techniques in between as long as you have good models. So it's really a space and performance trade-off. At high frequencies, the parasitics that I talked about earlier for the lumped elements, they dominate, and you can't really use surface mount lumped elements beyond a certain point. What point depends on the components. They're making surface mount components so small now that they're really hard to see. The 01005 components are really, really tiny. And then when you go onto integrated circuits, the parasitics are lower, so you can use lump matching to higher frequencies. So there's no one answer. One kind of rule of thumb is when the size of your component becomes an appreciable fraction of a wavelength, it starts behaving distributed, and it's going to be harder to use as a lumped component. Okay, so you can also solve this kind of a problem with analytical equations. And again, you guys have the notes. And this is, I use MathCAD. I mean, a lot of people use MATLAB. This is just a calculation sheet that is set up to calculate the solution to this analytical problem. If anyone's interested in and uses MathCAD, has access to it, and is interested in these sheets, I'll be happy to just send me an email, and I'll be happy to give them to you. So I could do this in ADS if I had ADS running, but I'll just kind of shadow it through here. So how would we maybe solve the problem in ADS? So we start out with a load. This one happens to be 25 minus J20. We plot it on the Smith chart. Well, we just simulate this at a particular narrow band, or that's what I did. I set up a narrow band sweep. So here's my load. So this is this position, right? Then I'm going to try to add a transmission line. Oh, by the way, this is actually just 3 different views of the same thing. This is what it looks like in the impedance. This is what it looks like. The admittance, it actually, you can see it's just kind of an inverted position of the chart in this admittance chart. In the immittance, it allows you to move shunt elements along these type of circles and series elements along these type of circles. So it's convenient once you really get comfortable with these two charts to put them together. So here is just showing after we add a transmission line of the right length, which we can use tuning. Since we're adding a shunt element, we want to be in the admittance chart like this, so that we're going to be on the G = 1 circle. So this is the result we want, and this is just the same view on the 3 different charts. And then what we're getting set up for is adding this length here to bring us into a match. Okay, and this is just another example with a shorted stub. It's just a different solution. The shorted stub is going to bring us the other way, so we have to come to this part on the G = 1 circle, so that if you remember one of my earlier charts, the shunt inductance is going to bring us up this way to the match. Okay, so finally, just very simply, a quarter wave transformer, the math comes out that if you have a transformer, if you're going from one real impedance to another real impedance, for example, from 25 ohms to 50 ohms, this formula right here will give you the characteristic impedance of a transformer that will give you a match. Okay, and that length will be 90 degrees long. But what if you have a little bit of reactance associated with your load? Well, you can still use a quarter wave transformer, but one way you can do it is first cancel that reactance. So you can cancel that reactance with an inductance first. Now at this point right here, I'd have 25 ohms if I pick the right value of inductance, and then I can use this same formula. So this just is showing going from the load position, rotating to the real axis, where from there, the quarter wave transformer takes me from this point to this point. So what we've done in this module is taken a brief look at lumped and distributed matching networks, and what I've tried to give you is some different tools. We've looked at analytical solutions where you can calculate the result. We've looked at the Smith chart. You can do this with a paper and a compass. That's old school. I come from old school. But you can also do the same thing in ADS, and as we heard from the other speaker, there's a convenient matching tool that probably makes it a lot easier for you as well. And the only way to really understand these solutions is to work problems. But I don't have any homework for you, so you guys get off the hook. There's some nice, there's a new YouTube tutorial from Housing Yap here I encourage you to go out and look at, and this is really the same thing. And if you want to explore, if you get the workspace, or if you didn't get the workspace and you want to get it from me, just here's my email address. And some of the models, like if you wanted to try our modelistics models, we'd be happy to set you up with a trial license to work with those. Okay, so I'm going to just roll right to our second presentation.